if the magnetic field can exert a force on a moving charged particle, then can a magnetic field exert a force on all of the charges that are moving through a wire? And the answer is yes. In this example, if we have a wire denoted by this black shape, and the current is denoted here with the arrow. So the current in the wire is coming out of the screen, and the velocity of the particles of the positive charge carriers that make up the current are also out of the screen. So if we put our thumb in the direction of the velocity of those charged particles, which is out of the screen, and we're in the presence of a magnetic field. There's a north pole and a south pole. Magnetic field goes from north to south. Then the force on those moving positive charged particles is going to be this way, out of my palm. So there's a force that tries to push that wire this way. So that's just what I've shown you here with my right hand, the thumb in the direction of the current, fingers in the direction of the magnetic field, and force out of the palm in the direction of the force on that wire. So this is a demonstration of this effect. This is a demonstration of the force on a current-carrying wire. Power stations need to bolt their high current wires down. And the reason is, if there are magnetic fields around and currents, those wires that are carrying the currents can experience large forces from the magnetic fields. What I have here is a battery, and what I'm going to do is touch this piece of copper to this piece of copper to complete the circuit. But the bottom line is I will have a current in this red wire. It's just a jumper cable wire. A current that will be in this direction. And magnetic fields produced by these horseshoe magnets that are horizontally toward me. And so the current, put my thumb using the right hand rule, put my thumb in the direction of the current in the wire, my fingers in the direction of the magnetic field of either one of these magnets, and the force on this wire will be directly upward. So what you'll be looking for, not only, I'll do it a couple of times so you can see the spark as these two things come together, because I've got essentially zero resistance in this circuit. I don't want it to run very long or I'll burn the wires up. But just a spark, a tiny jolt of electricity through that wire should be enough to pop it up. You know what? I'm going to turn on the battery, and that will help this work really well. So now with the battery on, so a little bit of spark here where we complete the circuit, and then the amazing jumping wire. And that's the force on a current carrying wire. A second demonstration. This is a demonstration of the force on a current carrying rod. What I've got here is a power supply and a piece of metal. I think it's aluminum, doesn't really matter. What does matter is that it's conducting. And it rests on two rails. This rail here and this rail here. The power supply is connected to this rail on the front side, and then the current comes out of the power supply into this rail, up into this rod, crosses over onto the other side and passes through this rail and then back into the power supply again. What we also have is a large magnet here. It's quite powerful, and its north pole is up and its south pole is down, so its magnetic field lines are pointing vertically upward. So using the right hand rule, we can point our thumb in the direction of the current through this rod, which is toward me, away from you. So my thumb is pointing in that direction. My finger is pointing up in the direction of the magnetic field lines. And then the palm of my hand points in the direction of the force that this magnetic field will exert on this current carrying rod. So it should push that rod in this direction. So it's a kind of a fascinating demonstration of the force on a current carrying wire. Okay, let's put some mathematical flesh on the bones. Derive the force on a wire segment carrying current I in the presence of a magnetic field B. We're going to start from the force on a moving charged particle, F equals QVB sine theta. So this is something we already know. And we're going to write this charge, since we're talking about not just a single charge, but a lot of charges, replace that Q with the delta Q. That's an amount of charge that passes. Then we're going to divide and multiply this equation by delta T. So here's where we've multiplied by delta T. Here's where we've divided by delta T. And you'd say, well, don't those two just cancel each other out? And I say, yeah, sure enough they do. So this is the same equation as that. But now in rearranging it in this way, we can see that there's a delta Q divided by a delta T. Well, that's a charge divided by time. And you say, well, that's a current. And I say, you're exactly right. So there's a current here. And then of distance times, a velocity, that's the speed of the moving charged particles, times a time, distance times a time will give a velocity times a time will give a length. And so this is a distance that those charges go in a time delta t. And that is the length of the wire segment. All right, putting it all together, this delta Q delta T becomes I, this V delta T becomes the length, and the magnetic field times the sine of the angle come along for the ride. The direction of the force is given by the right-hand rule with the thumb in the direction of the current. That's the direction of motion of positive charge carriers, right? And the fingers in the direction of the field, magnetic field, and the force is pointing out of the palm like we've talked about. So in this particular case, we have this rod coming out of the board at an angle, our fingers, our thumb in the direction of the current in the rod, our fingers in the direction of the magnetic field, which is in this case the red arrows to the right, and then our palm gives the direction, out of our palm gives the direction of the force, which is up in this case. One more demonstration of this effect, kind of a pretty one. This is a demonstration of the force on a current carrying filament. I have an incandescent bulb here with filament in it that lights up when you turn the power on. It's alternating current. So sometimes the current will be going up through the filament and other times it'll be going down. When it's going up, and when we apply a magnetic field, which is in this direction toward you, so I'm just going to be bringing this magnet close to the filament. If the current is up, I put my thumb in the direction of the current, put my fingers in the direction of the magnetic field, which is toward you, and the force on that filament will be the direction that comes out of the palm of my hand. So it'll be out this way. So it'll be a force in that direction to your right. When the current goes down through the filament, half a cycle later, the current now is down. Magnetic field is still in the same direction provided by this magnet, and the force then is in the opposite direction to your left. So what will happen is that this filament will oscillate back and forth 60 times a second in response to the static permanent magnetic field here. So this is it's a fun demonstration not only of the force on a current carrying wire, but also a demonstration of the fact that the current that comes out of your wall socket is alternating, goes back and forth. Okay, an example. The force and acceleration in a loudspeaker. And this is a pertinent example to everybody's lives. We all have speakers here and there. A voice coil of a speaker has a diameter of 0.025 meters and contains 55 turns. So this is just a coil of wire. It's a solenoid. It's attached to a speaker cone. And so that coil of wire and the speaker cone vibrate back and forth. That's the whole idea for a speaker, is to create that vibration that sends sound through the air. There's a very special shape of a permanent magnet that's used, very clever, with its north pole in the center and its south pole all the way around the outside. So magnetic fields begin on north poles and end on south poles. So we're talking about a magnetic field here that's radially outward through a gap in this magnet through which the voice coil passes. So what happens is if we take a vertical slice of this particular case, it looks like this. Here's the north pole sliced down the middle, south pole, and then this voice coil, the windings are shown with these dots and X's. So this winding, this is a wire that's coming out of the screen, and this is a winding of the wire where it's going in. So the windings are coming out like this, in like that. Okay, so what's the direction of the force? Well, all we need to know is the direction of the current in the wire and the direction of the magnetic field. Magnetic field points out, so let's look at this one. Put my thumb in the direction of the current, which is out of the screen. Then I want to orient the fingers in my right hand so they point in the direction of the magnetic field. That's given by this red arrow. So I want to rotate my hand if my fingers are down, and then the force acting on that wire segment is going to be out of my palm to the right. But the same thing happens here on the other side. So in this case, the current is into the board, the magnetic field is up, and the force is in the same direction. So all bits of current all the way along here feel the same. The direction of the force is the same for all of them. And so effectively then we can find the entire force if we know the entire length of the wire. And in each case, the magnetic field and the current are perpendicular to each other. So that sine of theta factor, the angle between the sine theta bit right here, that's the angle between the current and the magnetic field. Well, in this particular case, that angle is always 90 degrees, so we'll have sine of 90. All right, we have everything we need to put it together. You know what the mass is, et cetera, et cetera. So here's the formula, ILB sine theta, which looks like QVB sine theta for a particle. This is ILB for a length of wire. We put in the current, which is a given. This is the total length of wire in that voice coil. How so? Well, if you have wire that goes around in a circle, we're given the diameter of the circle is 0.025 meters. That's the diameter of the circle. The distance around a circle is what we call the circumference. It's 2 pi r is the way I normally remember it. But 2 times r is the diameter. So it's just pi times d, where d is the diameter and this is the diameter. So pi times the diameter, that's this part here. That's the circumference of one of the windings of wire, times 55 windings gives us the total length of wire inside of that voice coil. Then the magnetic field, a sine of 90 is just 1, and that gives the actual force, which is a pretty good sized force on that voice coil. And then force is mass times acceleration. And solving that for the acceleration, we can find that acceleration. It's a pretty good size acceleration, well over 9.8 meters per second squared. The idea in designing a speaker is to make this as light as possible, so it will accelerate very quickly in response to those changing fields, changing currents in the voice coil. And so it'll give as true as possible replication of the original sound. Loop of wire passes between the poles of a magnet, viewing the circuit from above. Let's do this one quick, it's not that hard. When the switch is closed, so we're going to close this switch. We've got a battery. We've got a magnet here with its north pole here and its south pole here, and its magnetic fields to the left is shown. What's the movement of the wire between the poles of the magnet? Well, we're going to have to know the direction of the current. Well, we know how to find the direction of the current. This is the positive terminal of the battery, the long line. This is the negative terminal. That means the current, which is the motion of positive charges, they're going to be repelled by that positive terminal. The current has to be in this direction. So the current, as it passes down through this magnet, is in this direction. And all we have to do to find the force is put our thumb in the direction of the current, our fingers in the direction of the magnetic field, just to the left on the screen, and then the palm of our hand pushes in the direction of the force on this current carrying wire, which is into the screen. So into the plane of the diagram, away from us. So that'd be the one that captures the answer there.